Okay, so is it true or false that if the only negative weight edges in the director graph are outgoing from the start node, the Dijkstra will compute a correct shortest path tree? Okay, so the whole issue with negative weight edges is that Dijkstra's algorithm assumes that the first time you really encounter that vertex, and you add it to the visit set, you're assuming that all the other ones they're gonna be requiring more edges or more cost because you're assuming that you know any any other path you take, the first time you get there, you're assuming that any other like path you really take, I mean, it has to be a longer path because what Dexter Cyclone is assuming is that they're all positive weights. So, but the thing is that that's only like later down the line. If the negative weights are only outgoing from the start node, that really shouldn't be an issue. So this would still be true. Suppose we run Dijkstra's algorithm from start node in an unweighted graph. What do we know about the shortest path between any two other nodes, U and V? Okay, so there can only exist a shortest path from U to V. So this wouldn't be the case because you know um, for any for this has nothing to do with Dijkstra's. Just you can have two nodes that have multiple shortest paths from each other, right? That should be pretty obvious, assuming that there's just two paths that have like the same total weight, like there's a cycle or something. And then a shortest path from U to V must include one more edges than the shortest path from tree S. This wouldn't be true because the shortest path tree, starting at S, only guarantees all the edges that get you from S to every other edge in the shortest possible. Um, so it's very possible that the shortest path from U to V could have have edges that are on that tree. So this wouldn't be true. If the shortest path tree reaches U and V, then U and V are connected. So this would be true because it's undirected, but um, at least you can get from U to S to V or V to S to U. So that would be true. And then the distance of a shortest path from U to V cannot be greater than the distance to dot get U plus the distance to dot get V. Yeah, so um, in other words, um, you can't, it wouldn't make sense that a shorter path would be larger than a path we already know, which would be U to S to V. So yeah, this would be true. It just wouldn't make sense that there would be a shorter path than that's greater than a path we already know. So yeah, it just wouldn't make sense. We consider this implementation to exercise algorithm uses a special min priority queue with the following asymptotic runtimes for each operation in terms of n. Size of priority queue. Okay, add its linear, remove its linear, contains and change priority are constant. Okay, um, so first off, you know, the worst case scenario is that in our priority queue, the parameter, it has every possible, you know, like every possible vertex in our parameter. Like we started at like some vertex and like that edge has like like all like that all the vertex is connected to like every other vertex or something, and eventually lead to a parameter um with every possible vertex. So while the parameter is empty, I'm going to remove the min, which is linear time. So essentially what's going on each time is you're um you're looping through the full perimeter and you're moving one each time. Since you're looping through the whole perimeter, this is going to run and you're moving one to each time. This is going to run magnitude of, or the number of vertexes. But every time it runs, you're assuming that the perimeter is full, you're gonna get a um, linear time removed min, and that removed min, the priority queue is gonna have, in the worst case, the amount of vertexes elements. So then you're gonna get the amount of vertexes squared just from this, and each time, for every vertex you get to, you have to look at all its edges. So in total, in overall, in total, after you went through all the loops, not just looking at this, but you went through all the whole while loop. You're gonna go through, in the worst case, like every single edge. That is the amount of edges. Okay, so this can you can essentially read this as like just for like the amount of edges. Do these certain operations. So then um you have an add at most you can at most you're adding all the possible vertexes once. So this doesn't really matter. And change priority is 1. So what you're gonna get is you're gonna get number of vertexes squared, magnitude of v squared, and then you're gonna loop through every single edge in total. So then you're gonna, and then you're gonna do the change priority, which is constant time. You're gonna add every single vertex at least once. So you're gonna get magnitude of v squared plus the total amount of edges, and yeah, that's the runtime for Dijkstra's.